In Part 9 of Lecture 2, we will discuss symmetric multiprocessor operating system concerns. A number of techniques can be incorporated into operating system software to support fault tolerance. A number of examples will be evident through the course. The following list provides examples. Process isolation. As was mentioned earlier in this lecture, processes are generally isolated from one another in terms of main memory, file access, and flow of execution. The structure provided by the operating system for managing processes provides a certain level of protection for other processes from a process that produces a fault. Concurrency controls. Lectures 5 and 6 discuss the difficulties and faults that can occur when processes communicate or cooperate. These lectures also discuss techniques used to ensure correct operation and to recover from fault conditions, such as deadlock. Virtual machines. Virtual machines provide a greater degree of application isolation and hence fault isolation. Virtual machines can also be used to provide redundancy, with one virtual machine serving as a backup for another. Checkpoints and rollbacks. A checkpoint is a copy of an application's state saved in some storage that is immune to the failures under consideration. A rollback restarts the execution from a previously saved checkpoint. When a failure occurs, the application's state is rolled back to the previous checkpoint and restarted from there. This technique can be used to recover from transient as well as permanent hardware failures and certain types of software failures. Database and transaction processing systems typically have such capabilities built in. A much wider array of techniques could be discussed, but a full treatment of operating system fault tolerance is beyond the scope of this course. In an SMP system, the kernel can execute on any processor, and typically each processor does self-scheduling from the pool of available processes or threads. The kernel can be constructed as multiple processes or multiple threads, allowing portions of the kernel to execute in parallel. The SMP approach complicates the operating system. The operating system designer must deal with the complexity due to sharing resources like data structures and coordinating actions like accessing devices from multiple parts of the operating system executing at the same time. Techniques must be employed to resolve and synchronize claims to resources. An SMP operating system manages processor and computer resources so that the user may view the system in the same fashion as a multi-programming uniprocessor system. A user may construct applications that use multiple processes or multiple threads within processes, without regard to whether a single processor or multiple processors will be available. Thus, a multiprocessor operating system must provide all the functionality of a multi-programming system, plus additional features to accommodate multiple processors. Key design issues include simultaneous concurrent processes or threads, scheduling, synchronization, memory management, and reliability and fault tolerance. Simultaneous concurrent processes or threads. Kernel routines need to be reentrant to allow several processors to execute the same kernel code simultaneously. With multiple processors executing the same or different parts of the kernel, kernel tables and management structures must be managed properly to avoid data corruption or invalid operations. Scheduling. Any processor can perform scheduling, which complicates the task of enforcing a scheduling policy and assuring that corruption of the scheduler data structures is avoided. If kernel-level multi-threading is used, then the opportunity exists to schedule multiple threads from the same process simultaneously on multiple processors. Synchronization with multiple active processes having potential access to shared address spaces or shared I/O resources, care must be taken to provide effective synchronization. Synchronization is a facility that enforces mutual exclusion and event ordering. A common synchronization mechanism used in multiprocessor operating systems is locks, described in Lecture 5. Memory management. Memory management on a multiprocessor must deal with all of the issues found on uniprocessor computers and will be discussed later. In addition, the operating system needs to exploit the available hardware parallelism to achieve the best performance. The paging mechanisms on different processors must be coordinated to enforce consistency when several processors share a page or segment and to decide on page replacement. The reuse of physical pages is the biggest problem of concern. That is, it must be guaranteed that a physical page can no longer be accessed with its old contents before the page is put to a new use. Reliability and fault tolerance. The operating system should provide graceful degradation in the face of processor failure. The scheduler and other portions of the operating system must recognize the loss of a processor and restructure management tables accordingly. Because multiprocessor operating system design issues generally involve extensions to solutions to multiprogramming uniprocessor design problems, we do not treat multiprocessor operating systems separately. Rather, specific multiprocessor issues are addressed in the proper context throughout the course. The considerations for multi-core systems include all the design issues discussed so far regarding SMP systems. But additional concerns arise. The issue is one of the scale of the potential parallelism. Current multi-core vendors offer systems with up to 8 cores on a single chip. With each succeeding processing technology generation, the number of cores and the amount of shared and dedicated cache memory increases, so that we are now entering into the era of many-core systems. The design challenge for a many-core multi-core system is to efficiently harness the multi-core processing power and intelligently manage the substantial on-chip resources efficiently. A central concern is how to match the inherent parallelism of a many-core system with the performance requirements of applications. The potential for parallelism in fact exists at 3 levels in contemporary multi-core systems. First, there is hardware parallelism within each core processor, known as instruction-level parallelism, which may or may not be exploited by application programmers and compilers. Second, there is the potential for multi-programming and multi-threaded execution within each processor. Finally, there is the potential for a single application to execute in concurrent processes or threads across multiple cores. Without strong and effective operating system support for the last 2 types of parallelism just mentioned, hardware resources will not be efficiently used. In essence, then, since the advent of multi-core technology, operating system designers have been struggling with the problem of how best to extract parallelism from computing workloads. A variety of approaches are being explored for next-generation operating systems. We introduce 2 general strategies here and consider some details later on in the course. Most applications can, in principle, be subdivided into multiple tasks that execute in parallel, with these tasks then being implemented as multiple processes, perhaps each with multiple threads. The difficulty is that the developer must decide how to split up the application work into independently executable tasks. That is, the developer must decide what pieces can or should be executed asynchronously or in parallel. It is primarily the compiler and the programming language features that support the parallel programming process design. But the operating system can support this design process at minimum by efficiently allocating resources among parallel tasks as defined by the developer. One of the most effective initiatives to support developers is Grand Central Dispatch, or GCD, implemented in the latest release of the Unix-based Mac OS X and the iPhone's iOS operating system. GCD is a multi-core support capability. It does not help the developer decide how to break up a task or application into separate concurrent parts. But once a developer has identified something that can be split off into a separate task, GCD makes it as easy and non-invasive as possible to actually do so. In essence, GCD is a thread pool mechanism in which the operating system maps tasks onto threads representing an available degree of concurrency, plus threads for blocking on I/O. Windows also has a thread pool mechanism since 2000, and thread pools have been heavily used in server applications for years. What is new in GCD is the extension to programming languages to allow anonymous functions called blocks as a way of specifying tasks. GCD is hence not a major evolutionary step. Nevertheless, it is a new and valuable tool for exploiting the available parallelism of a multi-core system. One of Apple's slogans for GCD is "Islands of serialization in a sea of concurrency." That captures the practical reality of adding more concurrency to run-of-the-mill desktop applications. Those islands are what isolate developers from the thorny problems of simultaneous data access, deadlock, and other pitfalls of multi-threading. Developers are encouraged to identify functions of their applications that would be better executed off the main thread, even if they are made up of several sequential or otherwise partially interdependent tasks. GCD makes it easy to break off the entire unit of work while maintaining the existing order and dependencies between subtasks. An alternative approach is to recognize that with the ever-increasing number of cores on a chip, the attempt to multi-program individual cores to support multiple applications may be a misplaced use of resources. If instead we allow one or more cores to be dedicated to a particular process, and then leave the processor alone to devote its efforts to that process, we avoid much of the overhead of task switching and scheduling decisions. The multi-core operating system could then act as a hypervisor that makes a high-level decision to allocate cores to applications, but does little in the way of resource allocation beyond that. The reasoning behind this approach is as follows. In the early days of computing, one program was run on a single processor. With multi-programming, each application is given the illusion that it is running on a dedicated processor. Multi-programming is based on the concept of a process, which is an abstraction of an execution environment. To manage processes, the operating system requires protected space free from user and program interference. For this purpose, the distinction between kernel mode and user mode was developed. In effect, kernel mode and user mode abstracted the processor into two processors. With all these virtual processors, however, come struggles over who gets the attention of the real processor. The overhead of switching between all these processors starts to grow to the point where responsiveness suffers, especially when multiple cores are introduced. But with many core systems, we can consider dropping the distinction between kernel and user mode. In this approach, the operating system acts more like a hypervisor. The programs themselves take on many of the duties of resource management. The operating system assigns an application a processor and some memory, and the program itself, using metadata generated by the compiler, would best know how to use these resources.